Ladies and gentlemen, boys and girls, my name is Mr. Do and science is my business. You are welcome to Mr. Do Science World, and today we're going to look at dynamics in physics. By the end of this lesson, you should be able to state and explain Newton's first law, Newton's second law, Newton's third law. You will be able to draw free body diagrams, and lastly you will be able to do calculations on the net force acting on an object. So let's begin with Newton's first law. According to Newton's first law, there are two versions of the Newton's first law which I'm going to explain. The first version of the Newton's first law states that if a body is at rest, that body will continue in its state of rest except an unbalanced force or an external force act on it for it to be able to change its state of rest. The second version states that if a body is in its state of motion on a straight line, that body will continue in a state of motion on a straight line except an unbalanced force act on it. Let's look at this law in the practical terms by making a demonstration by looking at this table. Let's look at the table. There is a mark on this table. If there is no external force acting on this mark, the mark will remain on its state of motion. For 2,000 years to come, it will remain here, except there is an external force to move this mark from where it is to another location. And that is the first version of the Newton's first law. The second version says, if the object is in its state of motion on a straight line, at a constant speed, the object will remain on that straight line except an external force act on it. So let's look at the mark again and see. The mark is in this state here. Immediately an applied force or external force is applied on this. You will see it moves from this location. It continues in its state of motion until another force acts on it for it to change its state of direction. Let's look at Newton's second law. According to Newton's second law, if a net force is applied on an object, the object will accelerate. The acceleration is going to be directly proportional to the net force and is going to be inversely proportional to the applied force. And this can be seen mathematically to say that there is a summation of the forces that are acting on the object. So we can see the sigma F standing for the sum of forces acting on an object, which is equal to MA. And MA, where the M stands for the mass and A stands for the acceleration with it the object is what is moving with. So let's look at it and see again. This sigma F simply implies the sum of forces. That simply means that what? We can say the sum of forces is being represented by what? By F net. And F net therefore is equals to what? ME. This is what Newton is telling us. Now let's move on to look at Newton's third law and see something about Newton's third law. Newton's third law is telling us that to every action there is equal and opposite reaction. It simply implies if a body A exerts a force on a body B B will also exert a force which is equal in magnitude but opposite in what? In direction to what? To the force A. That means that F1 is equal to negative F2, where F1 is the force exerted by the body A, and F2 is the force exerted by the body B. They are equal in magnitude, but they are opposite in direction. The important thing about this law you have to take note of is that when you see the negative sign, the negative sign does not tell you the magnitude, but it rather tells you about what? The direction of the force. Okay, let's look at the normal force. We're going to look at two scenarios: the normal force on a plane surface and a normal force on an inclined plane. Okay, so look at the first scenario where we have a normal force. A normal force simply implies a force which is perpendicular to a surface. So the force that is perpendicular to a surface is the normal force. So in a situation like this, we can see we have a plane surface like the table, and there is a body which is resting on this table. The body is resting simply implies that the body is not moving. Therefore, we can talk about two forces acting on this body. We can talk about the downward force and an upward force. The upward force is referred to as the normal force, and the downward force is referred to as the weight. So when you look at these two, we can see the object is not moving, and that is the interesting thing about physics. The object is not moving tells us that the object is at equilibrium, which means the normal force is equal to the weight. Therefore, Fn is equal to mg, which simply implies the normal force being equal to the weight. Now let's look at the situation where we have what? The inclined plane. On an inclined plane, the normal force is not equal to the weight. The normal force is perpendicular to the incline, and there is a weight which is at a certain angle to the inclined plane. Therefore, the normal in an inclined plane is equal to the perpendicular component of the weight. And that is the difference between an object being on a plane surface and an object being on a what? On an inclined plane. So let's look at it and see from here. On a plane surface, the normal force is equal to mg, but on an inclined plane, the normal force is equal to the what? Is equal to the weight multiplied by what? The cost of the angle. Okay, now let's look at free body diagrams. And to look at free body diagrams, I am going to make different scenarios or different demonstrations to explain to you the different types of free body diagrams that we can have, so that whenever you are given any situation, you will be able to draw the free body diagram. Alright, first let's understand what we mean by free body diagram. Free body diagram simply means a situation where you are drawing a diagram to show all the forces that are acting on an object. So let's look at the first scenario. A scenario where we are having a table, and this is a table, and we have a mass or an object or a body on the table. And when you look at it in this way, we can see that this body is exerting or is applying a force on the table, and the table is also applying a force on the one on the body. And in this situation, we can see that the body is applying a force in a downward direction to the table, and the table is also applying a force in an upward direction to the body. So to draw the free body diagram, we're going to have something like this. There are two forces that are acting because this body is not moving. Therefore, we have what? We have two forces that are acting on this. So the free body diagram, we are going to use a dot to represent the body or the mass, which is this. So Drawing the free body diagram, we're going to have something like this and something like this. Okay, I'm going to just explain something to you very important in physics. Now when I do this, we can see here is the Fn, which is the what? The normal force. In this case, the weight. So this is the normal force is the force that is being applied by the table on this body, and the weight is the what? Is the force that is being applied by the body on the table. So let's look at it and see. One important thing that we need to look at it in physics is that we can see the length of this arrow is equal to the length of this arrow. In case I'm not accurate in drawing, but you still have to just see that. And when you are drawing, you have to know that the length of this is equal to the length of this. And the reason is because the length of the arrow is representing the magnitude of the force. So, the magnitude of this force is equal to the magnitude of this force. That is the first scenario. Now let's look at a second scenario. We're still having this table again. This time around, we are having a force. Okay, so the body is placed on this, and we are going to apply a horizontal force by drawing this table. So I'm drawing the what? The object on the table. So we can see its movement. I draw it like this. Now, because I am pulling it this way, this is a rope, therefore there is a tension in this. So the tension becomes the applied force. So if I'm to draw the free body diagram, remember, this is still on the table, so there is still the normal force and the weight. The next thing that we're going to have is the what? Is the applied force. So let's assume there is no friction. This is a smooth table, so there's no friction. The applied force, which is the tension, is going to be here. And I put this T, which is the tension force. So this is longer than these two. The reason is because now this object is moving, telling you that this force is greater than these two forces. If there is a friction here, then we're going to have what? The frictional force acting opposite to the tension force. So it's going to go this way. You can put FR. It doesn't matter. Some textbooks use FR and the others use FF, telling you what? The force of friction. Now let's look at this and see. We can see that this is shorter than this because the force, the object is moving in this direction, telling me the force in this direction is greater than the force in this direction. Okay, another scenario. If I place this object again here, and I decide to apply this force in this direction, which means that the force now is at a certain angle, which means this force is having two components. It's having the horizontal component, which is the X component, and the vertical component, which is the Y component for this force that is applied. So I'm going to use this as the applied force. It can be a tension force or applied force, whichever way. So let's assume I am going to move this object. It can be moved in two different directions. It can be moved horizontally by the horizontal force or the horizontal component of this force, or so this way. Let's demonstrate that. You can see it's moving it horizontally. It can also go back and move it vertically by the vertical component of that force again. So you can see it moves it in this direction. I move it vertically. So draw free body diagram for the two situations. In all the two cases, I am going to consider friction. So if I'm considering friction, this is no longer going to be a what? A horizontal one. If I look at it in that case, remember that it was what? It was inclined at a certain angle. So that is going to be in this direction. Now call this T. which means that there is an angle which is here. And this force here, which is the what? The Tx, is the one that is moving the object in the horizontal direction. If I look at it and I'm trying to draw it where it's going to move it vertically, then moving it vertically, we're still going to have the same drawing in that same way, but this time around, it is not this part that is going to move the object, but what is going to move the object is the y component of this. So Ty is the one moving the object what? Vertically. So these are the two scenarios that we can have in such a situation. So this is a free body diagram, and we can see that in each case this shows us that there is a certain angle and there is this as well. We can have a situation where you've gone into the shopping mall and you are shopping. So you take your trolley and now you are moving with your trolley so that whenever you get to a place where you get an item that you need, look at it, I'm going in, I move it, I'm pushing, so I can put it in here like this. Remember, we said a force is a push or a pull. So we can have it in a situation where I am pulling or I am pushing. So if I am pushing it, then this is going to take this direction. So it's going to look like this. And we'll have it, the applied force in this direction, T here. And the friction is no longer going to be on this side, but the friction will go in this way. So I am pushing this way. So it can be a push or a pull. Take note of that. Alright. Now, what I said to you earlier is that in a plane surface, the normal force is always equal to the weight. Please keep that in mind. It's very important because our next thing that we are going to look at is a situation where we'll be looking at what? An inclined plane. Alright. Okay, so now let's look at the calculation of the net force acting on an object. We have looked at the different scenarios, so let's look at them. In a situation where we are having a free body diagram that looks like this, we're going to have F net according to Newton's second law is equals to MA. And F net is the sum of the forces acting on an object. What is the force here? It is Fn. And what is the force here? It is the weight, Fg. And this must be equals to Ma. But remember we said this force is equal to this force. The magnitude of these two forces are equal. And if they are equal, it simply implies that they can cancel out. So which means that the net force in this situation is equal to 0. The reason why it is 0 is because the object is not accelerating, so therefore acceleration is 0. And if acceleration is 0, if you multiply the mass by the acceleration, we're going to have the net force to be equals to 0. Let's look at the second scenario. We have TA, which is the applied force, which could be the tension, plus the normal force, plus Fg, and that must be equals to Ma. And remember, in this case, Fn and Fg are equal but opposite in direction. So if Fn is equals to negative Fg, it simply implies that here this becomes 0. And if that is 0, what we have here is going to give us what? Ta is being equals to what? Ma. Which simply implies that our net force is equal to the what? Is equals to the applied force. So here TA is equals to F net equals to MA. And that is it in this scenario or this situation. Let's look at the situation where we are having a friction. So we are saying that there is a friction. We know that the horizontal forces are not working, so they are equal to 0. Therefore, our TA plus FF is equals to MA. And remember, the F is a frictional force, which is opposite to this according to Newton's third law. So you're going to have it as TA minus FF equals to MA. And this is also very important when we are dealing with the calculation of the net force. Let's look at a situation where we have the angle being, the applied force being inclined. So if the applied force is inclined, we are going to have the horizontal part of the applied force, the vertical part of the applied force. So which simply implies we're going to have a right angle triangle. And if you're having a right angle triangle, which simply implies we can apply our trigonometry and make use of our SOHCAHTOA. So if we are making use of SOHCAHTOA, this simply means that we look at where the angle is. The side which is opposite is the side, that is the FAY. The side which is the adjacent is the FAX. So I need to find FAY and FAX, and then we can do the calculations from there. So if I do that, finding the FAY, we'll say that it is the opposite, so therefore we're going to make use of our opposite hypotenuse, because sine is opposite over hypotenuse. So we're going to say that sine theta is equal to opposite, which is FAY over hypotenuse, which is the FA. And what we are looking for is the what? Is the FAY. Therefore, making FAY the subject of relation, we're going to have FAY being equals to FA multiplied by sine theta. And this is very important that we have to make use of. So now if you're looking for the vertical forces in this, we can see the force here plus the force here must be equal to the force here. So we can say that our force, which is the upward force, must be equal to the downward forces. And there are two forces that are upward. So our FAY plus FN must be equal to FG. And from here we can just simply make use of our net force according to Newton's second law to say that our F net is equals to MA. And that means that F net is this plus that plus this. So we have FAY plus FN. If I transpose this to that, I will have negative FG being equals to FA. And this is very important in the calculation of the net force. So now I have found the what? The net force in the what? In the vertical direction. So we can just simply say F net Y. F net Y. And that is what we are having here. Let's look at the horizontal forces. On the horizontal forces, we can see from this point that the normal force and the weight are not working because they are equal in magnitude, so they are going to cancel themselves, because if this is positive, this is negative. If this is negative, this is positive, and they're going to cancel out. So the only force that is going to keep the object moving horizontally is the frictional force and the FAX. So let's find the FAX. Our FAX is simply going to be our applied force, and you can see this is adjacent. So we're going to make use of what? Cos theta. And that becomes cos theta. So which means that FAX is equals to our FA cos theta, which is very important. Now we're going to make use of the net force application. So our net force we know is equals to MA. Look at it. F net in the x direction is now FAX and the frictional force. So FAX is here, so I'll say it is FAX, which is opposite to the frictional force, so minus the frictional force is equals to FA. Then what is FAX? It is what we have here. Therefore, our net force can simply be FA cos theta minus our our FF being equals to MA. And this is also the net force acting in the horizontal direction. Right. So these are the scenarios that we can have. But remember that this is when we are pulling the force. If you are pushing it, it's the same thing that we're going to have. The only thing you have to know is that the diagram, the free body diagram, is going to change, where we're going to have the frictional force moving in this direction and the applied force moving in this direction. And that is the only thing that makes the difference between these two ways of the calculation. But the net force remains the same. In our next lesson, we're going to look at inclined plane. And I will say at this point that thank you very much for watching this video. And then look out for part 2 of dynamics in physics, and we are going to start or begin with inclined plane, calculations with the inclined plane.